Hello, everyone. In this video, we'll define what it means for a matrix to be invertible, and we'll start thinking about why that's an important notion. Let's get going. The idea behind invertibility of matrices comes from the fact that you can think of matrices as operations that transform vectors. We've seen this idea at work when we defined the product of two matrices. If you keep thinking about that, then you may find yourself looking for another matrix that undoes the transformation done by a matrix. And that's exactly the idea behind an inverse. More formally, what we would like to find, given a certain matrix A, is another matrix B that undoes what A did. In other words, then, if I transform a vector with A, and then I apply B to the result, I get back the initial vector. In other words, their product is the identity matrix. We don't want to just do it in one sense, but we would like that also if I transform a vector with B, and then I transform the result with A, I get back the initial vector. So we require for an inverse to satisfy these two equalities, that AB is the same as the identity, is the same as BA. If this happens, if such a B exists, we say that the matrix A is invertible, and we'll write that B is A to the minus 1. We read that A inverse. The reason why we use this minus 1 comes from the idea that an inverse is kind of dividing by in the real numbers. When I have a real number or scalar, an exponent minus 1 just means 1 over that scalar. And when I multiply A times A to the minus 1, I get exactly 1. This equality here is what resonates with us because now we have that A times A inverse is equal to the identity. However, you should you should keep in mind that 1 over a matrix is not defined. So the notation is only suggested. Let's try to look at an example of inverse matrices. If I give you two matrices like this, the way you want to check that they're inverses to one another is by multiplying them in both ways and see the result you get. So if I multiply A times B, I get the following. This is 2/5, 3/5, and 1 over 5. Let's multiply them. The first entry is minus 1/5 plus 6/5. That's 1. Here I get minus 2 times 1/5 plus 1 times 2/5. That's 0. The third entry up here is 3 over 5 times 3 times, 3 over 5 plus 3 times minus 1/5. That's also 0. And 2 times 3/5 is 6/5, minus 1/5 is 1. Let's do it the other way around. 2/5, 3/5 minus 1 over 5 multiplied by 1, 2, 3, 1. So when I multiply these, my first entry is minus 1/5 plus 6/5. That's this times 1 plus this times 2. That's 1. And then let's compute the others. Minus 1/5 times 3 plus 3/5 is 0. 2/5 minus 2/5 is 0. And at last, we get 6/5 minus 1/5 is 1. So these two matrices are indeed inverse to one another. Some of the next questions that we'll think about inverse matrices are, well, the first of all, how do you know how to find B given A? So in this example, I gave you the inverse, but in general, how do we find the inverse? Is it true that inverses exist? How do we know when they exist? And the third question is the one that I will try to answer in this video, is why do we care about finding inverses. Before we move to the how do we care, let's try our luck with the first two in our little example. So how did I come up with B in this example? Here's one way. We don't know what B is, so we don't know what the entries A, B, C, D of our matrix B are, but we know what we're looking for. We're looking for them to multiply to the identity matrix. So when we take this product, we can easily compute it to be the following. This is A plus 3C. Then the second entry here is A plus 3B. Then we have 2A plus C. And then we have 2 times B plus D. And this gives us 2 sets of linear systems. Something's off. This should be first row, second column, B and D. So we get 2 linear systems. The first one is A plus 3C must match the entry in the identity matrix, which is 1, and 2A plus C is equal to 0. The second is B plus 3D must be 0, and 2B plus D must be equal to 1. I'll let you solve these linear systems, but you'll find that the result must be the matrix B that we worked with before. Let's get to why it's important to think about inverse matrices. And the answer again lies in the fact that we are building this new theory to solve linear systems. So it's maybe not surprising that I will set up a scenario like this, where I have a vector X, which is my vector of unknowns. And by applying a matrix, I get something on this side, A times X. And we're supposed to know what that image is. So we're supposed to know B. That's exactly the problem of a linear system, AX equals B. Now, suppose you want to solve this linear system and you don't know what the vector X is, but maybe you know what the inverse matrix is that undoes this transformation. Well, in that case, you're in luck, because saying that AX is equal to B is the same as saying that X is A inverse applied to B. The reason why that's true is the following short computation. If I have that AX is equal to B, I can multiply both sides on the left by A inverse, like so. But then A inverse times A is the identity, so this side becomes just X. The identity times X, which is just X. In other words, what I'm saying is that if you know the vector of constants and you know the inverse matrix, then it's really simple to compute the solution to your linear system. Let's do that in the example that we've been working with in the set of nodes. Here we have a matrix A, and we computed the inverse before. So we can solve AX equals B for any choice of B just by doing one simple matrix multiplication. I'll pick one random value for B, which is 1, 5. But then if I want to solve this linear system, AX equals 1, 5, that's the same as computing A inverse times 1, 5. And that's something that we can do really fast, because it just amounts to multiplying this matrix. Oops, this is a 5. Times 1, 5. Let's do it. The result we get is minus a fifth plus 3 and 2/5 minus 1. That's your solution. That's your vector X. So you see why it's important to know how to handle and work with the inverse matrices. Let's have a look at some properties of inverse matrices. There's these 3 essential properties. If a matrix is invertible, then its inverse is also invertible, and the inverse of the inverse is the matrix itself. This is very plausible if you think in terms of undoing operations. If you have two matrices that are both invertible, then their product is also invertible, and the inverse of the product is the product of the inverses, but again, notice the change in order. AB inverse is B inverse A inverse. We'll think more about this property in a second. Let me just comment on the third. If a matrix is invertible, then so will its transpose. And the transpose of the inverse is the inverse of the transpose. It's all very natural. Let's go back to think about the matrix B, the property B. Remember that the inverse that we want is a matrix that undoes AB. So if I think of AB in terms of I do B and then I do A, well, when I want to undo that, well, let's focus on this equation here. I do B and then I do A. So when I want to undo that, I will have to undo A and then undo B. So let's try our luck with saying that C is B inverse A inverse, and we'll check it. It makes sense that it is because of this undoing business. And in fact, what we can compute here, I'll just check this side, is an application of the associative property of matrices. I can move the parentheses by the associativity, and then I'll use the fact that A inverse and A are inverses. So this is the identity, and it goes away. And therefore, B inverse times B is the identity as well of the correct size. We can try to compute the other order to check that C is an inverse on both sides, but the computation is the same. We have B inverse times A, but B inverse is the identity, so I lost an inverse. This is A inverse, which is again the identity. Okay, we can iterate this property B to the product of many more matrices, but we need to keep in mind that whenever we take the inverse, we need to reverse the order. So if I have three invertible matrices A, B, C, and I want to take the inverse of that, this will be C inverse times B inverse times A inverse. And I can do this a number of times. If I have a bunch of matrices A1 through AN that are all invertible, then their inverse will be just the product of all the inverses in the reversed order. Okay, this concludes the properties of invertible matrices. We'll see next time what theoretical consequences inverses have for us.